Ever had that moment, you're at the beach, bite into your sandwich, and ugh, gritty sand.
Oh, yeah, definitely. Not pleasant.
Or maybe you've just watched honey, like really slowly drizzle off a spoon.
Hypnotic, isn't it?
Totally. Well, believe it or not, those little moments, they touch on some really fundamental science, and that's exactly what we're diving into today.
That's right. We're doing a sort of whirlwind tour
Yeah.
looking at 10 mini experiments, the kind you might vaguely remember from school science lessons.
Yeah, like a quick look at some core ideas.
Exactly. Think of it as a super quick, hopefully insightful look.
We've got the sources here outlining these 10 experiments, and our mission really is to pull out those key aha moments.
Mhm.
We want to give you a clear sense of the principles, maybe point out something surprising and, why it matters, all without getting too bogged down in jargon. Ready to jump in?
Absolutely. Let's kick things off with that beach scenario you mentioned, separating sand and salt.
Okay, so the challenge, you've got this mix of sand and salt. Maybe a wave did it, who knows? How do you actually get them apart?
Right. Well, the trick is knowing they have different properties. This first experiment uses a pretty neat method. First step, you take your mix, add some water, and stir it gently.
Okay, gently. The source asks, why gentle?
It's simply to help the salt dissolve in the water. Salt dissolves, sand doesn't. Simple as that.
Right, makes sense. So now you've got salty water with sand floating, well, sinking in it. What's next?
Filtration. That's the key here.
Yeah.
You pour the mixture through filter paper in a funnel.
Okay.
The source diagram shows it. Well, the sand grains are too big. They get stuck in the paper.
They get left behind.
Exactly. And what passes through?
Right.
That's your saltwater solution, the filtrate.
Got it. Filter paper acts like a superfine sieve. So wet sand in the paper, salty water in the beaker. How do we get the dry salt back?
Last step, evaporation. The instructions say to gently heat the salt water, maybe in an evaporating dish, until it starts to spit a bit.
Spit. Okay, sounds like you need to be careful.
Yeah, there's a caution note, don't get too close. Hot spitting salt isn't fun. But the source asks, why heat it?
To get rid of the water.
Precisely. To evaporate the water, leaving the solid salt crystals behind.
Brilliant. So from a messy mix, you get pure sand and pure salt using water, filter, and heat. What's the big takeaway?
Well, this seemingly simple thing demonstrates really fundamental separation techniques. It's all about solubility stuff, dissolving, and different states of matter. Solid, liquid, gas.
And these ideas scale up, right? Like for purifying water or something?
Absolutely. Same basic principles, just on a much bigger scale in industry.
Okay, let's move to experiment 2. Viscosity. It's a word we hear, but what's it really about?
Think of it as a liquid's resistance to flowing. Its thickness, as the source puts it.
Like the honey example.
Exactly. Honey or treacle flows slow, high viscosity. Water flows easily, low viscosity. Even gases have it, though we don't usually notice.
So how does this experiment let us see viscosity? It involves bubbles.
Yeah, it's quite clever. You get tubes of different liquids washing up liquid, water, oil, shampoo, stuff like that.
A nice variety.
Then you flip the tube, get an air bubble at the bottom, and time how long it takes that bubble to rise to the top.
Ah, okay. And the idea is the bubble moves slower through the thicker, more viscous liquid.
That's it. More viscosity means more resistance to the bubble moving. The table in the source is for recording the time for each liquid.
So you can directly compare. Longest time means most viscous. Shortest time means least viscous.
You got it. The bubble has to sort of push its way through.
Like wading through treacle versus water. Makes sense. The source also challenges the listener. How else could you compare viscosity? Any ideas?
Oh, that's a good one. Well, you could just try pouring them, couldn't you? See which flows fastest from the same angle.
Yeah, simple observation.
Or maybe drop a small identical bead into each one in time how long it takes to sink. Same principle, different direction.
Cool. So why does understanding viscosity matter in the real world? It's not just bubbles and tubes.
Oh, definitely not. It's crucial. Think engine oil needs the right viscosity to lubricate without causing too much drag.
Right. Too thick or too thin would be bad.
Exactly. Or in cooking, the viscosity of a sauce affects its texture, how it coats food. Even blood viscosity is important for health. It pops up everywhere.
Okay, on to number 3. The rate of evaporation. We know puddles dry up, liquids disappear without boiling. What's the science there?
That's evaporation in a nutshell, liquid turning to gas below boiling point. This experiment looks at what makes it happen faster or slower, using propanone.
And it tests a few different things, like spreading it out versus a blob.
Yep. Spread versus unspread drop. Also cool versus warm temperature. And still air versus moving air, like using a fan or just blowing on it.
Lots of variables, and there's a table again to record the evaporation time for each condition.
Right. The how-to is quite detailed, warming the slide, using a matchstick to spread the drop. And a key safety note. Propanone's flammable, so no flames nearby, and wear eye protection.
Good advice. So let's unpack the whys. Why does spreading it out speed up evaporation?
More surface area. Simple as that. More molecules at the surface have a chance to escape.
Okay, and warmth.
Heat gives the molecules more energy, more kinetic energy. So more of them have enough energy to break free from the liquid.
Right, more energetic molecules escape easier. What about moving air?
Moving air, like blowing or a fan, sweeps away the vapor molecules that have just evaporated.
Ah, so they don't hang around and condense back.
Exactly. It keeps the concentration gradient high, encouraging more evaporation.
So it's all about giving molecules the chance and the energy to escape. What's the key principle here? The source mentions cooling.
Yes, that's a really important point. Evaporation is a cooling process. When the fastest, highest energy molecules leave, the average energy of the ones left behind drops.
And lower average energy means lower temperature.
Precisely. That's why sweating cools you down. Same idea.
Fascinating stuff. Okay, number 4. Chromatography of leaves. You mentioned hidden colors. I always just see green.
Well, the green is mostly chlorophyll for photosynthesis. But leaves have other pigments too. Paper chromatography is a neat way to separate them out.
How does that work? It starts with grinding leaves.
Yep. Chop up some leaves, grind them with a bit of sand and propanone. The propanone dissolves the pigments. The sand helps break the cells open.
So you get a colored liquid extract. Then what?
You take chromatography paper, draw a pencil line near the bottom, and carefully put tiny drops of your extract on that line, letting each dry. You build up a small concentrated spot.
Okay, a tiny dot of color.
Then you hang the paper in a beaker with a shallow layer of propanone at the bottom. Crucially, the solvent level must be below your spot.
Right.
The propanone then travels up the paper by capillary action. That's the mobile phase. The paper is the stationary phase.
And it carries the pigments with it, but why do they separate?
Because they have different characteristics. Some pigments dissolve better in the propanone, some stick more strongly to the paper.
So it's like a race.
Kind of. The ones that dissolve well and don't stick much travel furthest up the paper with the solvent. Others lag behind.
And you end up with different colored bands.
Exactly. Once the solvent nears the top, you mark where it reached the solvent front, take the paper out, let it dry, and voila. Your chromatogram shows the separated colors.
Amazing. So the colorful paper is the result. What colors might we see besides green?
You'll see different greens, sure, different chlorophylls, but often yellows and oranges too. Those are carotenoids. They were there all along, just masked by the green.
Wow. So what's the core scientific idea here?
It's a beautiful demonstration of separation based on physical and chemical properties, solubility and adsorption, fancy words for dissolving and sticking. Chromatography is used everywhere in science to separate complex mixtures.
Right. Okay, experiment 5 moves into energy changes. The energetics of freezing. Things get cold when they freeze, obviously, but is there more to it energy-wise?
Definitely. Changing state, like freezing, always involves energy transfer. This experiment looks at the temperature as molten sodium thiosulfate pentahydrate, quite a mouthful, turns solid.
How's it done? Melting and then cooling?
Yeah. You gently heat the crystals in hot water until they melt. And take the tube out, let it cool, maybe put some cotton wool on the top, and stick a thermometer in. You watch the temperature as it cools and starts to solidify.
And you're looking for the freezing point temperature.
That's part of it, yes.
Yeah.
But the source asks 2 key things. Is freezing exothermic releasing heat or endothermic absorbing heat?
Things get colder, so maybe it absorbs heat? No, wait.
It feels colder to us because it's losing heat to the surroundings, but the process itself is exothermic. As the molecules lock into the solid structure, they release energy.
So freezing actually gives out heat. That seems weird.
It does seem counterintuitive. That release energy is why during the actual freezing process, the temperature might plateau, stay constant for a bit, even though it's in a cooler environment. The heat being released balances the heat being lost.
Okay, that explains the plateau often seen on cooling curves. What about the second question? Why does the temperature drop again after it's all solid?
But once everything's frozen solid, there's no more energy being released from that phase change. So the solid just carries on cooling down towards the temperature of its surroundings.
Got it. So freezing releases energy, which temporarily holds the temperature steady, then it continues cooling.
Exactly. Phase changes are all about these energy transfers.
Right. Let's switch gears to something practical. Experiment 6, the accumulator. Sounds like batteries.
You got it. An accumulator is just a rechargeable battery. This experiment uses a simple lead-acid cell, like a basic car battery, to show how they charge and discharge.
How does the experiment work? Charging and then seeing how long it lasts?
Pretty much. You connect the cell to a DC power supply, 4.5 volts here for different times, like 180 seconds, maybe up to 300 seconds. That's charging, storing energy chemically.
And discharging.
After charging, you disconnect the power supply and connect the cell to a small light bulb. Then you time how long the bulb stays lit.
Ah, so more charging time should mean the bulb stays lit longer?
That's the expectation, yes. The source has a table for charging time versus time bulb is lit, and it suggests plotting a graph.
What would that graph likely show? A straight line?
You'd expect a positive correlation, more charge time, more light time, but probably not a perfect straight line. There are always inefficiencies, energy lost as heat,
Makes sense. There are also safety warnings about sulfuric acid and lead. Important stuff.
Very. Lead compounds are toxic, so wash hands thoroughly. Sulfuric acid is corrosive, causes nasty burns, definitely need eye protection.
Good reminder. So what's the key concept this accumulator experiment shows?
It's the basic principle of rechargeable energy storage. Electrical energy converted to chemical energy during charging, and then chemical energy back to electrical energy during discharge, and how input relates to output.
Cool. Okay, number 7, electricity from chemicals. Also sounds like batteries.
It is. It's about how different metals react differently and how we can use that reactivity difference to generate electricity. You basically build mini cells.
Using strips of metal. Which ones?
The experiment uses zinc, copper, lead, iron, and magnesium. You take pairs of these, stick them into a sodium chloride solution, the electrolyte.
That lets ions move.
Exactly. And then you measure the voltage between the two different metal strips with a voltmeter.
So each pair makes a tiny voltage, like a battery.
Precisely. The more reactive metal wants to lose electrons more, becoming the negative terminal. The less reactive one becomes the positive terminal. Electrons flow from negative to positive through the voltmeter.
And the voltage reading tells you something about how different their reactivities are.
Yes. The bigger the voltage, the bigger the difference in reactivity between the two metals in that pair.
So the source asks us to rank the metals by reactivity based on these voltages. How?
By comparing the voltages systematically. If, say, magnesium paired with zinc gives a bigger voltage than zinc paired with copper, it tells you magnesium is more reactive than zinc, which is more reactive than copper. You build up the whole series that way.
Clever. So you don't need to see them actually reacting, just measure the voltage potential.
Right. It demonstrates the fundamental idea behind all electrochemical cells, turning chemical reactivity differences into electrical energy.
Let's shift focus completely. Experiment 8. Iron in breakfast cereal. Seriously. Metal in my cereal.
It sounds weird, but yeah, many cereals are fortified with tiny amounts of actual elemental iron powder for nutrition. This experiment tries to fish it out.
How on earth do you do that? With a magnet?
Exactly. You need a strong magnet. One way is to float some cereal on water and see if the magnet can pull the pieces around.
Might be tricky to see.
It can be. The other method is usually better. Crush the cereal into a really fine powder, spread it on paper, and then move the magnet underneath the paper.
And the iron particles should stick to the paper above the magnet.
They should follow the magnet as you move it, yeah. You might see tiny dark specks moving.
Wow. Now, the source asks an important question. Are all metals attracted to magnets?
Good point. No, they aren't. This only works because iron is ferromagnetic, strongly attracted to magnets. Metals like copper or zinc wouldn't be pulled out this way.
Right, it's specific to iron. The source also connects this to iron deficiency symptoms. Why?
Just to give context, iron is vital for carrying oxygen in our blood. Not enough leads to anemia, feeling tired, weak. Fortifying cereal is one way to help people get enough iron.
So it's a health thing, not just a weird ingredient. The takeaway is some foods literally contain metals for nutritional reasons.
Exactly. A direct link between chemistry and health.
Okay, nearly there. Experiment 9. Unsaturation in fats and oils.
Yeah.
We hear about unsaturated fats being good. What does this experiment show?
It uses bromine water, which needs care. It's harmful and irritant, so eye protection is a must.
Noted.
It uses bromine water to compare how unsaturated different oils are, like olive oil versus animal fat. Unsaturation means the fat molecules have carbon double bonds.
Double bonds. Okay. And how does bromine water test for those?
Bromine readily reacts with those double bonds. When it reacts, the reddish-brown color of the bromine water disappears.
Ah. So if an oil has lots of double bonds, is very unsaturated, it will react with and decolorize more bromine water.
Precisely. You dissolve a bit of oil in a solvent, then add bromine water drop by drop, shaking until the color stops disappearing and stays yellowy-brown.
And you record how many drops or the volume it took?
Yes. The oil that needs the most bromine water before the color stays is the most unsaturated. The one needing the least is the most saturated, or least unsaturated.
The source says this is approximate and asks how to improve it. Any thoughts?
Well, you'd want to use exactly the same mass of each oil and make sure the bromine water concentration is consistent. Doing repeats and averaging would help too.
Makes sense for better science. It also asks what unsaturated means chemically.
It means the carbon chains in the fatty acids aren't fully saturated with hydrogen atoms. They have one or more double bonds between carbon atoms instead of all single bonds.
Got it. So this experiment gives a visual clue about the chemical structure of fats.
Exactly. Connects the chemical structure to a reaction you can see.
And finally, experiment 10, the pH scale. Acids, alkalis, neutral. How does this experiment explore that?
It uses universal indicator solution to estimate the pH of different everyday substances. Remember, pH 7 is neutral, below 7 is acidic, above 7 is alkaline or basic.
And universal indicator changes color depending on the pH.
Yes, it's a mix of indicators, so it gives a whole spectrum of colors, from red for strong acids, through orange, yellow, green for neutral, to blue and violet for strong alkalis. You add it to your test solution and compare the color to a chart.
So you get an actual pH number or a close estimate?
Pretty much. The record is the substance, the color, and the estimated pH.
The source asks us to classify things as acid, alkaline, neutral. Easy enough. But why use universal indicator instead of simpler litmus paper?
Litmus just tells you acid, red, or alkaline blue. It's very basic. Universal indicator gives you a much better idea of how acidic or alkaline something is at strength, because it gives you that approximate pH value across the whole range.
More informative. Okay. And the last question. What happens if you mix an acid, like vinegar, with an alkali, like lime water?
That leads to a neutralization reaction. The acid and alkali react, canceling each other out, chemically speaking.
And the pH changes.
Yes, the pH moves towards neutral, towards 7. Vinegar, acetic acid, and lime water, calcium hydroxide, would react to form calcium acetate, a salt, and water.
So this last experiment is a practical way to measure acidity and alkalinity using indicators and the pH scale.
Exactly. A fundamental concept in chemistry with relevance everywhere.
Wow, that was quite a sprint through 10 experiments. From separating sand and salt through viscosity, evaporation, colors in leaves, freezing energy, batteries, metals and cereal, fats, and finally pH.
It covers a lot of ground, doesn't it?
It really does. Hopefully for everyone listening, that sparked a few aha moments, or maybe just reminded you how much science underpins everyday stuff.
Absolutely. Each one, however simple it seems, demonstrates really core scientific principles used in all sorts of fields.
So maybe the provocative thought for today is, as you go about your day now, can you spot these principles in action? See separation techniques, notice viscosity, think about evaporation or pH.
Or even think about how that simple battery experiment scales up to power the device you might be listening on right now.
Exactly. What other everyday things could be explored with just a simple scientific experiment? Definitely something to think about.